recording yet. Okay. All right, this is Physics 1A for the March 10th or something like that, I think today is. And today we're going to do a couple problems. The first one is the one that you can see on the screen right here about a falling flower pot. We're just continuing to kind of make use of the stuff we learned yesterday, which is the kinematic equations that relate the velocity, position, and time at which an object is at that point to their acceleration, and they only work for constant acceleration, so we'll do a couple constant acceleration problems. All right, so the first thing we're going to do is I'm going to have you all kind of spend probably 3 minutes to try to think about this problem, write down some of the information we have, maybe draw a picture, and I'll also be drawing a picture at the same time. Yeah, so try to set it up. This problem has a lot of missing information, and you need to be kind of clever about how you go about solving it. So take a few minutes, read the problem, and write some stuff down, and I'll check back. Okay. That was enough time for you to think about kind of what needs to happen here. So, how do we want to approach this problem here? What kind of information do we know? Well, we know the time that it takes for this flower pot to fall, and so I basically just drew up a bunch of floors. Each floor is 4 meters high, so I try to make them the same size. I drew a little window here on this floor. I put the window at the top. I will say that it doesn't actually matter where you put the window. I think you get the same answer no matter what. Like, we could put the window here, we could put the window at the bottom, we could put it in the middle. I think you're still going to get the same answer. Because our question isn't about like exactly how high it dropped from, more what floor it dropped from. So there's some wiggle room there. Okay, so we kind of know, I would say 3 pieces of information, right? We know a time, and we know a distance, which could be a displacement, delta x or delta y. And then we also know one other thing. What other thing do we know in this problem that's not explicitly stated? We know the acceleration due to gravity, right? So this problem involves meters, right? So we're going to use that the acceleration is going to be, well, let's define an axis. Let's say that the up direction is positive y. Okay. Acceleration then is going to be negative 9.8 meters per second squared. So we know those. Usually when you know 3 pieces of information, you can do something. Now, in this case, I don't know that we can necessarily. Let's think about it. So what we also know, the pieces of information we'd be missing would be whatever the velocity of this object is right here. And I can't really, we'll just say it's going down, and its velocity at this location, let's call it like v1, and the velocity when it gets to here, I think I can probably draw it on here, right? When the velocity gets to here, let's call that v2 or something. We don't know what those values are. But there is one other piece of information in this problem that is given that I didn't explicitly write down. Does anyone know what it is? What else do we know? Sure, delta y is this 1.5 in this regime here, right? Let's actually just write down everything that we know for these 2 points. So what we know is delta y is going to be, is it positive or negative 1.5? It's negative because it's going down, right? The other thing we know obviously is the acceleration, which I wrote there. We know the time is 0.1 seconds. So what can we find now? What can we solve for? Can we solve for any of these variables? V final? I was thinking about V initial, which is V1, but just because we've got this equation, delta y would be equal to V initial t plus 1/2 at squared. We could find the initial velocity, right? We could also then find V final if you want to, Kelvin, afterwards. Or we could use the equation where it's like V final t minus or whatever if we want, but let's solve for V initial. So we're going to call this V1. We're going to call it V initial right here. All right, so we want to isolate that variable. So we'll do delta y minus 1/2 at squared, and then just divide by t to get V initial. Now I'm going to call this V initial just V1 for this part. So we'll erase that one. We're just going to call it V1. And the reason why will be pretty obvious soon. All right, Tom Gui, I don't think there's much value in just putting an answer in the chat. I mean, it's impressive if you've got the answer. I'm glad that you can work it out, but this isn't the kind of class where you're going to get credit for just blurting out. It'd be like, imagine if we were in a classroom and you just blurted out the answer. That's what that's like. I mean, no offense intended or anything like that. I'm sure your intentions are good and all, but you know, just try to contribute as we go, if you know what I mean. All right. Okay, so plugging in all the numbers for this. Here, let's move this calculation over here because we're going to need to draw some more things on this picture. All right. So delta y, we said was negative 1 at 1.5. Negative 9.8. And then time. And then divide by time. And this should all be equal to v1. So what do you all get if you calculate that? Can we do this one? Remember, of course, that just because there's a minus sign here, don't forget you have to, when you plug in a, it was negative, right? So negative 15.5. Are we okay with the fact that the answer comes out as negative? Can I get anybody else to kind of verify they get the same thing? Yeah, it's negative because it's going down, right? I don't see my phone near me, so I'm going to have to rely on you all to do the calculation. Let's see, so it's something like, it's like negative, so it's like 5 times 0.01, which should be 0.05. Yeah, that seems about right. You got a different answer? 14.5, is that what you got? That sounds more correct. It has to be less than 15, I think. 14.51, does everybody agree with that one? Okay, that seems reasonable to me, because if you just make this 10 and you do 5 times, or a half of 10, that'd be 5. 5 times 0.01 would be 0.05. We're subtracting this, so that should be 14.5, and then you divide by 0.1, it would be exactly 14.5 if it wasn't for the 9.8. Okay, so now we know what the velocity right here is. And if we know that piece of information, how can we then find what floor it fell from? And what is the other piece of information that I was mentioning earlier that we haven't written down yet? What is the other piece of information that we haven't written down yet? V initial equal to 0. What do you mean by that? Where is the velocity 0? And how did you know that? When it fall. Yeah, so it says which floor did the pot fall from, right? So the idea would be maybe there was some ledge up here that this flower pot was sitting on, and maybe a wind gust came along and like knocked it off, and it starts to basically fall straight down. And the fact that it's falling straight down means that it must have dropped from rest. So this means that when it says it fell from, that means it fell from rest, even though it's not explicitly saying it. So we know that the velocity at this location, the initial, is equal to 0. That's why I call this v1 and v2. Okay, so now what do we do? Now how do we figure out where it fell from? We'd like to know what the y-coordinate of this would be, basically, right? Like, what is y initial? That's basically what we want to know, right? Or put it another way, between these 2 points, from here down to here, we want to calculate delta y. So you want to use an equation for this interval, right? So we want to basically say we're going to take this piece of information and this piece of information. So we know the initial velocity and the final velocity. We also know the acceleration between these 2 points, right? So if it fell from up here, then we know the accelerations, obviously. So then we have 3 variables, right? 1, 2, and then we can use the equation that Tom put in the chat. So let's do that. So for the second part, we'll just use a different color. So we know delta y is what we're looking for. We know the acceleration. We don't know the time, but we know what I'm now going to call the final velocity is going to be v1, which is negative 14.51. And the last piece was what? V initial, right? V initial is equal to 0. So let's take that information and do a calculation. I tend to kind of write these, oops. Let's just box all this stuff in here to indicate that that's kind of a separate part of the problem. I tend to write these, what do you call it? I tend to do these little charts like this. I don't know what you want to call that. This little grid of information for every one of these problems every time I do a step. So when you do a new step, you got to kind of write a new set of variables and knowns. Do a new little chart right here for the new set. Don't want to use all the information from the previous part because now delta y has changed, right? And delta t has changed. You can't just use this time over and over again in the problem. Yeah, it's just a new problem, Kelvin, exactly, with their own set of variables. That's right. That's a good way of putting it. Okay, so the equation we want here is this one. V final squared is equal to V initial squared plus 2 times the acceleration times the displacement. And we're solving for the displacement, delta y. So rearranging this, we get Vf squared minus V initial squared divided by 2a. Should be equal to delta y. Okay, gotta be careful about negative signs here. So Vf was negative 14.51, so negative 14.51 meters per second. And then we square it. Minus 0 for the initial velocity. And we just solved this. You end up getting negative 10.7. Does everyone agree? So that would put it, so 10.7, right? So that would be, this distance from here to here is 4. And then that's 4. So that's, 2 floors at least. And then if you go another 2.7, which would be kind of like right about here. If we add all those up, you get 4 plus 4 is 8 plus 2.7. So the flower pot basically dropped from somewhere up here. And so we can rearrange that. It looks like it dropped from right about there, which is on the 8th floor, which is what you were saying, Ton. So it's a good job you got that right. So does anyone have any questions? That's kind of neat. We'll just circle the floor. That's the answer. I could have drawn more floors, Ange, but I ran out of room. I did not know. I didn't know it dropped. I didn't know it to begin with. It dropped from the 8th floor, Ange. So that's a really good question. I just drew enough floors above it that I felt like that might be enough. I actually couldn't remember if the answer was 7 or 8. I just knew it was. I knew it wasn't 9. So it's more about just the space that I had available on the screen because I didn't want to make the floors too small. I guess I could have started drawing from like the 4th floor, but I thought that might be confusing. So, yeah. Any other questions? If you'd like to, I see homework is more difficult, 3 question marks. Okay. What do you mean? You want me to do something harder? Is that what you're saying? Yeah, we'll do that next, man. It's too bad you think that problem's too easy because I bet a lot of people in this class don't think it's easy, and they probably appreciated us going through it. So you need to be really careful, Ton. Your language is... Like, the 3 question marks on there is really aggressive. It's really aggressive, dude. And we're all here to learn. You may already know all this stuff, and that's great. You may be really well prepared, but you need to be careful. This is an educational environment, all right? And while I understand that you may look at a problem and think it's easy, it doesn't mean that other people think it's easy. So You gotta be really careful, man. Okay, so this is a little more challenging problem. So we have a 40-foot long truck. It's traveling down the... How much time do we have left? We have plenty of time. Okay. A 40-foot long truck is traveling down the freeway at 70 feet per second at about 40... This doesn't matter. A car 10 foot long, so here's the car, has been following the truck 60 feet behind. So it starts off here. It's 60 feet behind the truck. Okay. And it says the truck in the front is traveling at 70 feet per second. The car starts to accelerate at 8 feet per second squared to pass the truck. And the truck driver starts to accelerate at 2 feet per second squared. The car cuts back into the right lane when it's 30 feet ahead of the truck. So that's what this picture represents. So the car basically accelerates to pass the truck. It passes the truck, and then it gets back. Like, think about it as like changing lanes. Like, it's in the left lane here, and it's in the right lane now. So it basically just cuts back in front of the truck. At that time, it's 30 feet in front. Now, if you'll notice these measurements. The first measurement is taken relative to the front of the car and the back of the truck. And the second measurement is taken relative to the back of the car and the front of the truck. So it's kind of reversed in a way. And that definitely matters. Okay, so we have two different objects. They're both accelerating. The car has an acceleration of 8 feet per second squared. The truck driver has an acceleration of 2 feet per second squared. And the car cuts back into the right lane when it's 30 feet ahead of the truck. We want to find how long does it take, and we also want to find the final speed of the car and the truck. That's what we want to do. So I'm going to give you all, let's do 4 minutes. So take 4 minutes and try to set up the problem. You don't need to solve anything. You just need to set it up and kind of try to think about what you would do to solve it. Yeah, so take 4 minutes, and we'll come back at like 2:30. I'll mention one other thing too, by the way, regarding the difficulty of the problems that we're doing in class. If you want me to do more difficult things, Ton, if you want me to work on hard things that are harder, then after the class is over, if there's a problem on the homework that you don't understand, you can ask me about it, and I'll be happy to show you how to do it. You can also show up to office hours and ask me about it, and I'll be happy to show you like steps and stuff on how to do it, right? Like I'm always available. I start every class by saying, "Do you have any questions?" I show up for all of my office hours. I haven't seen you at any of them. So if you're having problems on homework, please just ask. Oh yeah, absolutely, Paige. For sure. Definitely. Yeah, let's just do that after class today. Let's when the after the first hour is over, we'll just spend a lot of time kind of going through any problems that anyone has with any of the homework problems. I'm more than happy to. I love helping people with homework problems. It's really fun. Yeah, that's right, Ange. It's asking how long will it take for the car to go basically from the initial position to the final position. So it has to catch up to the truck, and then it has to get 30 feet ahead of it to get to this. Then the total time is what we want there. The length of the truck, it's gonna show up, but you need to just take into account that length base. I guess I would say when thinking about how far the car actually moves. Yes, you can do that, Hudson, for sure, and we will definitely do that. Yeah, you can basically pick a fixed point on each object, the car and the truck, and then use that point to represent the position of the object, right? And just be consistent. If you want to use the front of each, that works. If you want to use the back of each, that works. If you want to use the middle of each, you can do that too. Just got to be consistent, though. I do not believe that's correct, Tom. Read the question carefully. The initial velocity of the car is not zero. See, it says the truck is moving at 70 feet per second, and then the car, it says, has been following the truck. So you got to use that to figure out what the initial velocity of the car is. And if that doesn't make sense, imagine you're in a car and you're following a truck on the road and the truck's moving at 70 feet per second. What does that mean you're doing? Yeah, that's right. Same initial velocity. That's right. Should we find the initial what? Chase. That's it. That's the answer. The initial velocity is 70 feet per second. The idea is kind of like the truck. The car is like behind the truck, but keeping a distance of 70, 60 feet, and then it starts to accelerate to pass him, which I think is kind of how you normally drive on the road, right? If you're driving along the highway and there's a big truck in front of you, and maybe you want to pass it. The first thing you do probably is just to match speeds with it, and then you might change lanes and pass it when you feel like it's safe, right? Okay, that's about 7 minutes actually. Let's see what we can do to solve the rest of this problem. Speed, distance, and volume? You don't mean volume, do you? You mean acceleration? Okay, so first things first, as someone mentioned, yeah, that's right, Hudson. That's right. Okay, so the first thing to do here, as someone mentioned, is to kind of pick some points, right, to be the position of these objects, okay? So what I'm going to do is I'm going to choose the back of each object. So this point right here, I'm going to call the initial position of the car. So X initial for the, I guess, do we want to use C for car? I guess that's fine. Oh, you know what? We need to zoom in a little bit here because this is just a little bit too small of writing. Sorry. Let's see if this is better. Okay. So we're going to use this position here, the back of the car. We're going to call that the initial position of the car. And then we'll just always use the back of the car from now on. So the final position of the car, we're just going to say X final car is right there. And then for the truck, we'll also use the back of the truck. So this position here is going to be X initial for the truck. Use capital T. And then the back of the truck will be the final position. x final for the truck. So given that's what our definition is going to be, we want to write down equations for each of them. So we'll have, on the left over here, we'll have the truck, and then we'll have the car. And we're just going to kind of tabulate up all the information we have. So what we know is that from this position, as people were figuring out in the chat, that the car is also moving at 70 feet per second to begin with. And what happens at that point is that the car starts to accelerate. It says the car starts to accelerate at 8 feet per second squared to pass the truck. So the car has an acceleration that goes this way, which I'll call the acceleration of the car. And the truck has an acceleration that's a lot smaller, which I'll call the acceleration of the truck. So what we have is initial velocity, acceleration, and we've got some positions, and we'll see how those end up playing out as we do this. So let's write down all the information we're going to need here. There's going to be x initial for the truck. There's going to be x final for the truck. We're going to have the acceleration of the truck, which is given as 2 feet per second squared. There's the, what do we have? The initial velocity of the truck, the initial truck, which is 70 feet per second. And the other variables we would have, but we don't have the information, would be the time and one other piece, which would be the final truck. Those are the two things that we're actually trying to solve for. Okay. We don't really know what these guys are either. And we'll come back and talk about those two pieces of information. So we kind of just know two things basically, right? The acceleration and the initial velocity, and then some kind of relative distances that are written on this picture. For the car, the acceleration of the car was 8. The acceleration of the car has to be greater than the acceleration of the truck, or else it won't pass it. And the initial velocity of the car is 70 feet per second. Okay, so the first thing that Summer is saying, we need to set xt minus xc equal to 30 plus 40. Are you talking about the final positions or the initial positions? And you're certainly right. Final or the initial you're talking about there? I think you're talking about final, right? That's final, right? Yeah. So that's an equation we can write down, right? So what he's saying is that if we look at our picture right here, it's pretty clear that, like, let's say, for example, that the position right here, let's just pick a number. Let's say it was 100 feet, okay? Then the position of the car would be 100 plus 70, right? So that's an equation we can write down, right? We can say that the final position of the car should be equal to the final position of the truck plus 70. And you might be like, oh no, it's 30, right? But no, it's the whole distance between the back of the car and the back of the truck, only because we chose those. Like, I decided to say back of the truck is going to be what the position of the truck is. I could have chosen the front, and this equation would have been a little different. But you'd still get the same answer at the end. It doesn't matter. So yeah. So that's an equation we can use. That's very good. Can we write down another equation that's similar to this? X initial for the truck, you're saying, should be equal to X initial for the car, which was way over here, right? And then we have to add how much? It's 70, right? We want to add 70, right? Yeah, that's right. I knew what you meant. Okay, so there's a couple equations that we have. A couple equations there that we can use. immediately seeing another way we could do this. I'll just ignore what I'm thinking. Okay, so now what we need to do is we got to write some equations down. We have, from our equations over here on the right-hand side, we only have 2 pieces of information, but that's okay, because we know some information about how the truck is connected to the car, right? And one thing we know is that whatever the time is, these two are going to be the same variable, right? Whatever that is. So if we can come up with an equation that involves acceleration, velocity, time, and also involves these two, right, then we'll probably be able to connect them via these 2 equations here. Okay. We're also free to make one of these variables 0, right? You know what I mean? Any one of these positions, we can pick one to be 0. It doesn't matter which one we pick. So, yeah, let's use the one on the farthest right? We'll make that one 0. And now, actually, positive is going to the left in this picture. This is going to be positive x in this direction. So if we make x initial for the car equal to 0, then we also know what the x position for the truck is. It would be 70, right? Oops. From that equation right there. So now the initial position of the truck, if that's 0, the initial position of the truck just becomes 70. And now we're kind of off to the races. Now we can easily, not easily, but we can kind of see where we would solve this problem. So let's write down our 2 equations. For the truck, what we're going to have is delta x for the truck should be equal to the initial velocity of the truck times time plus 1/2 the acceleration of that truck times time squared. And then for the car, we're going to have delta x for the car is going to be equal to the initial car times time plus 1/2 acceleration of car times time squared. When we write down delta xt, we can actually rewrite it with this information up here. So delta xt is basically the final position. No, stop it. The final position of the truck minus the initial position of the truck is equal to all of this stuff. Do we want to start plugging things in? I think we probably do. So v initial t is 70 feet per second times t plus 1/2, and then acceleration of the truck is 2. Okay, and the other one we knew is this, that x final truck was 70. So let's go ahead and replace this with 70 right here. Okay, so we've got a nice equation here. How many unknowns do we have in this equation now? Oh, whoa, I did it wrong, right? Oops, yeah, absolutely, thanks for catching that. This is the one we want to replace. X initial for the truck, that's what we know. Okay. Then we go over here for the car and fill out the same information. So x final car, or delta x car is going to be, oh, there's something wrong right here. This should have been C, shouldn't it? So sorry about that. Okay. So doing delta x for the car would be x final minus x initial for the car. X initial is 0, so this is just equal to x final car. Yeah, we'll just write minus 0, just so it's clear that we actually made some kind of change. The initial for the car is 70 also. So people out there that are really clever may have figured out that there's a way you can make this problem even simpler by kind of noticing that if they have the same speed to begin with, they're both 70, right? Anyone have any idea what we could do to kind of maybe do kind of a shortcut? I'm not going to do it, but just if anybody's interested in trying another way to solve the problem. What could we have done? Okay, I'll let you type what you're typing out there, and we'll continue to solve this. All right, so what do we do next? We've got these two equations. How many unknowns do we have between these two equations now? That's funny. T, that's one variable. What else do we have? Yeah, that's right, Haiti, exactly. It's following the truck. Just imagine like you're driving down the road and you're just like keeping your distance from a truck. You'd be matching speeds, right? If the truck in front of you is going 60 miles an hour, you're also going 60 miles an hour. Yep. How many variables in these two equations, the blue one and the red one? There's two in the one on the right. There's an additional one, right? Like this is a variable. This is a variable. That's right, Joanne. It's 3. That's right. And t is a variable. There's 3 variables. So these two equations alone are not enough, right? But luckily for us, we have a third equation, right? 3 unknowns, you need 3. Maybe I wasn't being very clear there. But yeah, 3 unknowns, you need 3 equations, right? So now what we can do is we can use this equation, take it down to 2 unknowns, right? So what this equation says is that x final for the car is equal to x final for the truck plus 70. So let's just plug that in right here. So the right-hand side of our red equation now, we're going to use this one and say that x final for the car is equal to x final truck plus 70. And we'll do 1/2 of 8 is 4. Okay, now we're down to 2 unknowns. So basically what we can do is we can just kind of isolate this variable in both equations and then kind of set them equal to each other, right? So let's do that. So the left-hand side of this equation is going to become x final truck is equal to, we'll add the 70 to the right-hand side. One half of 2 is 1. And we do the same thing over here. So we subtract the 70 now. And now we can just set these two equations equal to each other. We'll use another color for that. Before I do that, does anyone have any questions? All right, we going a little too fast here. Okay, setting them equal to each other, we'll have... Yeah, we can just kind of copy paste them, right? All right, so this copy, paste, and we'll make a different color to indicate that we're kind of doing something a little bit different. So that needs to be equal to all of this. And then we can do some cancellations. So the 70 feet times t is on both sides of the equation, so it cancels out. And yeah, we just need to solve here. So we end up getting 70 plus 70, that's 140. And then on the right-hand side of the equation, we'll get 4 minus 1, which is 3. Divide the 3 over here, so 140 feet divided by 3 feet per second. Oh, wait. No. Wait a minute. Oh, feet per second squared. I was noticing that the units weren't going to work out. So all of this should be equal to t squared, which means we just need to square root this side over here. And we get rid of that squared. And people are saying that the answer 140 divided by 3 would be about 50, the square root of which would be about 7, and you're saying the answer is 6.8. So that seems reasonable. That seems reasonable. Technically, it's plus or minus 6.8. But there's really no indication that we shouldn't just take the positive root here. So that's going to be our answer. And yeah, that's the time at which the car gets to this position where it's 30 feet in front of the truck. We also want to find final velocity, but, we're pretty much done. So any questions? We want to find final velocity of both of them. So here, let's move all of this over to the left so we have some room. So what I would do is basically, let's see. Oh no, that's not at all what I wanted to do. Okay. So for v final truck, we can use the v initial truck plus acceleration times time. So the final truck should be 70 plus its acceleration, which was 2. And then we multiply by 6.83. So if you all could calculate what this is, it's going to be about 55 or something like that. Oh, you add, right. So sorry. Yeah, 83, about 84. We'll say 83.66. That's fine. And then, of course, we could do the exact same calculation for the car. And that's it. Does anyone have any questions?
I got a quick question, Professor. My bad.
Yeah.
So the two equations that we first begun with that are in the red boxes, x final of the car and x initial of the truck. How'd you guys end up figuring out to also include the x final of the truck or the x initial of the car? Because let's assume we're gonna do the top one, x final of the car equals x final of the truck plus 70.
Yeah.
Coming from my thought, I would assume that actually, I'm kind of lost in why would you include x final of the truck, honestly?
So here, what I noticed is that when we come to write out our equations right here, and then maybe even farther when we get to this position here, there's just some information that's missing. So like I said, when we look at those two equations, there were 3 unknowns, right? So we needed something that related x final car to x final truck, right? But if you look at when you look at the picture, they're related to each other, right? They're 70 feet apart from each other.
Yeah.
So that's the reason I knew to do it. Is because we needed some other equation to relate these, otherwise we couldn't really solve them.
Okay.
That's a good
Thank
question.
you.
Yeah, no problem.
Shimurda,
Yeah.
in the beginning, you found that delta xt equals v, the initial. You found that one kinematics equation.
Yeah.
I'm asking, because I know how to pick equations, but this one,
You're breaking up a lot. I couldn't really follow the question completely.
Can you hear me?
Oh, I can hear you.
Can you hear me?
You're just kind of breaking up. Could you type the question out, maybe? I'm gonna stop the recording for now.